Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's Scribblecast of Organic Chemistry Lectures and Solutions to Homework Problems. In this lecture, we're going to be doing some sample reaction problems that typify the kind of questions that you can get concerning the substitution reaction mechanisms, SN1 and SN2. We're going to be focusing on pure reaction problems. That is, you're given a reagent, some more reagents over an arrow, and you have to draw the products. Some of the things I will be drawing here will actually be structures used in obtaining the final solution. So you actually wouldn't draw them as part of the final solution. You might do them on a scrap piece of paper. Also take note that the questions could be changed. You could be given one reagent and a product and asked to put the second required reagents over the arrow. I'm not going to do any of these at this time, but you could easily change these questions and to do so. And I might, if I think of it, draw attention to that. So let's begin with some simple reaction problems. And I'm going to start with a simple small molecule here, such as methyl bromide. And methyl alkyl halides, we learned when we look at our mechanisms, prefer to undergo SN2 reactions, no matter whether you hit them with strong or weak nucleophiles. So whether I hit this with H2O, which is a relatively weak nucleophile, or hydroxide, which is a relatively strong nucleophile, I get the SN2 reaction mechanism, and they produce the same product. In this case, backside attack in the SN2 will cause the bromine to leave, and in the case of water you end up with a protonated alcohol which quickly deprotonates. In the case of hydroxide acting as a nucleophile, you get the alcohol. But both eventually produce methanol by SN2. I do not have to worry about the inversion of the chiral center because the center I'm looking at is not chiral. If, however, I provide you with a chiral center, such as this molecule, and I might draw it thusly, where I actually show the chirality in 3 dimensions, you have to be concerned about inversion. But note the center is not only chiral, but I have shown the specific chirality. If you have a chiral center where I do not show it, for example, well, I'll show you that in the next case. Let's draw it here. If I draw it this way, the same molecule, in the bottom structure, yes, the center is chiral, but I haven't shown chirality. This could be R, it could be S, it's not shown. Although inversion does occur at the center, you don't have to show inversion for an SN2 mechanism. For an SN1 mechanism, you get racemization. And I would not have to draw the racemate because I did not require it by drawing a 3D type structure. I did not show the chirality. For interest's sake, if we prioritize, the bromine's number 1, the ethyl's number 2, the methyl's number 3. If I project the H to the rear, that's 1, 2, 3, this center is S. Now let's do a couple reactions with this, and let's use some different nucleophiles. For example, I could use water, or I could do a reaction where let's use the molecule methoxide. In fact, instead of water, we did water up on top. Why don't we change this and use, well, I don't know, methanol. Okay, let's try that. Now, whenever you're confronted by a reaction, the first question you always ask yourself is, what kind of alkyl halide do I have? In the first question, we answered that. We said methyl bromide. We had a methyl halide. What kind of alkyl halide do I have? Well, some of the things that jump into your head is it's chiral. The molecule's chiral, it's S, it's a bromide. But when I say what kind of, I'm not really after any of those features. What I'm really asking, is it primary, methyl, secondary, or tertiary? So is it methyl, primary, secondary, tertiary? We look at the carbon bearing the halide, and if it has 2 carbons attached to it, as this is a secondary alkyl halide. And then I have to remember my trends. Methyl and primary only react by the SN2 mechanism. Tertiary only reacts SN1. Secondary, however, can react by either reaction mechanism. They can react either SN1 or SN2, so we have to go on. In fact, as secondary alkyl halide, I now look at the nucleophile. If the nucleophile is a weak nucleophile, it will favor SN1. Methanol is a solvent molecule. The SN1 in this case is often called a solvolysis reaction because you're using solvent as the nucleophile, and the nucleophile is fairly weak. Because of this, it will favor the SN1 mechanism. So this will typically go SN1. Now, since I have shown the chirality in a 3D structure, you would have to ask yourself, okay, he's shown the chirality. What does SN1 do to an enantiomerically pure compound? What does SN1 do to a chiral center? Well, SN1 gives you a racemate. And because of that, you would draw a racemic mixture. So, what is the nucleophile? What actually adds to the molecule? Well, SN1 gives you a carbocation. And the nucleophile in this case is the oxygen binds, giving you an OCH3. It's actually in the protonated version. And then the proton leaves. So it looks like we've produced a chiral ether. And now I'm going to draw, because it is a racemate, the other enantiomer. Running out of room here, so I'll draw this way. And you get a 50-50 mixture of these two, or what we've known as a racemate, a racemic mixture. So SN1 would racemize our chiral center. If we look at the bottom reaction, a secondary alkyl halide can go either SN1 or SN2. Methoxide is a strong nucleophile, so it favors SN2. We can throw it in an aprotic solvent. We might use acetone, for example, to help continue the favoring of the SN2. And SN2 gives inversion of the chiral center, so I would have to draw the inverted product for backside attack. Okay, so notice that shows inversion of the chiral center. If I check the prioritization, I would get, in this case, 1, 2, 3. This guy's R. Now be careful. Inversion can go from S to R. But you can still have inversion and go from S to S if there's a change in prioritization. What do I mean? Well, suppose, theoretically, I had instead of an ethyl, I had a fluorine. So let's just check that. Fluorine's less basic. It's a poor leaving group. So instead of the ethyl, there was a fluorine there. If I prioritize the bromine, bromine's number 1, fluorine's number 2, methyl's number 3. If I drew my arc projecting number 4 to the rear, it would be S still. In the product, this would have been fluorine. The reason the inversion went from S to R was the prioritization number 1 bromine was also prioritization 1 for an ether. But if you switch to fluorine, the ether's no longer 1 because fluorine's higher atomic number than oxygen. Fluorine would be 1. Oxygen would be 2. Methyl would be 3. And if you did that, you'd still have S. So you'd still have inversion, but the inversion process also gave a prioritization change. And hence the prioritization change leads to S inverting into a new S. So don't always think inversion must give you R. You can find examples of chiral inversion in an SN2 reaction where S will go and stay S. All right? So be careful when you look at this. Don't just simply say inversion, S must be R. Look at it carefully. Now let's do the bottom one, and let's do this with methoxide, or let's do hydroxide again. What would you draw for hydroxide or H2O? Well, this is the same molecules up on top, except we're not showing the chirality of the chiral center. And if in the reagent I don't show the chirality, you don't have to worry about the inversion or racemization either. In other words, you know that you have a secondary alkyl halide. You know you have a strong nucleophile. You know that favors SN2. Well, even though it favors SN2 and you should show inversion, because I didn't show the 3D nature, I didn't show the chirality, you don't have to. And so you can just draw the product. But you know, because it went SN2, that if you were given the chirality, you would get the inverted product on the chiral center. Okay, let's try another way that you might have chirality shown to you. It might not be drawn as a 3D structure. You might, for example, be given it in a fissure. I might, for example, give you your sec-butyl. Let's make this one iodide this time. And I might give it to you. It's like this. And let's use a different nucleophile. Now, I'm going to write, sometimes we actually write on nucleophiles with their counterions. Because, you know, reagents, you can't just grab an anion. There's usually a counterion. So don't be confused. You might just write sodium cyanide. I know sodium is positive, so cyanide must be negative. Nucleophiles are negatively charged to neutral species, okay? If they have a counterion, they're negatively charged. The nucleophile is the cyanide. Don't put sodium on as replacing the iodine. And let's take a look at this. I have sec-butyl iodide. What kind of alkyl halide do I have? I have a secondary. Secondaries can go either SN1 or SN2. So now I look at the nucleophile. Sodium cyanide. Is it a strong or weak nucleophile? Well, hopefully you've memorized your trends in nucleophilic strength, and you know cyanide is a very powerful nucleophile. And hence, strong nucleophiles on secondary favor SN2. So this is going to go SN2. I've shown you the chirality in a fissure projection, so you must draw the product in the fissure, showing what happens to the chiral center. SN2 takes chiral centers and inverts them, so the hydrogen's going to swing to the other side. Get the H here, and the cyanide attaches through the carbon. Excuse me. And you produce this product. And there's inversion of the chiral center. Okay, how about this chiral center? What about bromide? And let's try it with the weak nucleophile. Oh, let's change that a bit. Why not? Let's go that. So suppose you come along and you take a look at this chiral center and you say, oh, it's a bromide. I've shown the chirality. This is a weak nucleophile. Weak nucleophile favors SN1. So what does SN1 do to chiral centers? SN1 gives you racemization. The nucleophile will replace the bromine. The H will leave, so you'll have an ether, OCH3. And you get a racemate with SN1. Now hopefully you're sitting there in disbelief, and hopefully you've seen what's wrong with this. What did I forget to do? I forgot to check what kind of alkyl halide I had. I just jumped in, started taking shortcuts. Okay, look at the nucleophile. The nucleophile's weak, SN1. What kind of alkyl halide is this? Look at the carbon. That carbon that bears the bromine only has one carbon to attach to it. It's primary. What mechanism do primaries react? Primaries go SN2, irrespective of weak or strong nucleophile. So, we don't just get, we go SN2, we don't get racemization. What do we get? We get inversion. We get this guy only. Why? Because we go SN2, because it's primary. Be careful. Be careful. Check carefully so that you can identify what is going on. Okay, let's raise the ante a little bit and complicate things a little in these reactions, going beyond the chirality. How about what goes on when you have a molecule like this? What happens if I take this molecule and say react it with hydroxide? Well, again, the center I'm looking at is chiral. Okay, so I may have to watch that, but I didn't show the chirality, did I? So whether I go SN1 or SN2, I'm not concerned about racemization or inversion. I'll just draw the product because I haven't shown chirality. That's good to know. What kind of alkyl halide do I have? Well, this carbon has 2 carbons. It's secondary. So I have to look at the nucleophile because secondaries can go either SN1 or SN2. Okay, I have next a hydroxide. What can the hydroxide do? Well, hydroxide's a strong nucleophile, so it favors SN2. As I've stated, SN2 gives you inversion. And so I don't have to worry about that. I can just replace the bromine because I have not shown the chirality. And I can just quickly draw the product where the OH replaces the bromine. I know it's inverted, but since I didn't show it in 3D structural fissure, you don't have to. Okay, let's try it with H2O. Well, again, we have a secondary alkyl halide, but this time we have a weak nucleophile. Weak nucleophile means SN1. Okay, SN1. SN1 produces a racemate, but again, I didn't show chirality, so I don't have to worry about it. And I just draw my product. And I draw the same product as I did for SN2. And this is where we have upped the ante a little bit and made it complicated. There is a factor that I'm adding now to SN1 that you must do from now on whenever you have an SN1 structure. SN1 goes through a carbocation intermediate, and you must always draw that intermediate on scrap paper and look at it closely. So pull the bromine off, put the positive on the carbon where the bromine was, make a carbocation, and look closely at it. What kind of carbocation is that? It is a secondary carbocation. It has two carbons attached to the carbon bearing the positive charge because it formed from a secondary alkyl halide. Now we must check for the possibility of step 2 from our SN1 reaction mechanism, the possibility of rearrangement. Rearrangement means to shift an atom or functional group from an atom next door, so an H or a methyl. For example, you might try a 1,2 methyl shift. In which case, this methyl, we're going to just jump it over. We're going to shift it. So I'm going to take this methyl and have it jump over to where the positive of is. And it takes its bonding electrons with it. And when it does so, the positive is now gone from here. The methyl shifted, so this guy's positive. When you do a shift, you must always look at what kind of carbocation you've now made. Well, this carbon is positive. This carbon has two carbons attached to it, so it's secondary. Shifting will only occur if you produce a more stable carbocation. So you must ask yourself the question, who is more stable, secondary or secondary? Well, obviously they're the same. So this shift would not occur. Okay, that would not occur. And is there anything else I could try shifting? Well, there's the H. I could try shifting the H over. So let's try a 1,2 hydrogen shift. And I'm going to shift this H over, which would leave that methyl originally there. So I shifted the H and I get this carbocation. What kind of carbocation do I have? Well, this carbocation, this kind of carbocation, this carbon with the plus has 1, 2, 3 carbons. It's tertiary. Are tertiary carbocations more stable than secondary? If you remember your lecture on the SN1 reaction mechanism, you will remember indeed they are. Due to inductive electron donation, the positive is more stabilized. This shift will happen because you actually get a more stable carbocation. A more stable carbocation. Now, this shift happens rapidly. It is at this point that the nucleophile will attack. So the nucleophile comes in, water adds where the positive is, it deprotonates, and you get this. So our product that we should have drawn should have been this guy. Now, are they the same? Well, if I was to name this, we have 1, 2, 3, 4 carbons, a 2-butanol with a 3-methyl. This guy is 3-methyl 2-butanol, or butan 2-ol. What about the bottom molecule? 1, 2. It's 2-methyl-2-butanol. It's a different molecule. The top one does not form. Because of the shift, the correct product is this guy. So you see how 1-2 shifting can change the outcome of a reaction. You must always be careful. You must always check for 1-2 shifts. Okay, given that, let's try a few different molecules and see what we can come up with. How about something in a chair conformer? We haven't drawn chairs recently for a little while. What if my alkyl halide is in a chair conformer? Say, like this. And what if I hit it with hydroxide? Oh, let's try something, a strong nucleophile. How about SH minus, a very powerful nucleophile, the thiolate anion? What kind of alkyl halide do I have? Well, there are, and I'll put dots on my carbon so they're all clearly shown in the ring. Sometimes when I shrink these videos for PSPs and iPods, it's hard to see where the carbons are. Well, that carbon that's bromine, there's 2 carbons attached to it, so it's secondary. Secondary alkyl halides can go either SN1 or SN2. And so I have to look at the nucleophile where the nucleophile is very strong, so it's favoring SN2. So did I show chirality? I get inversion of chiral centers. Well, look, this carbon has a CH2 and a CH2, a CH2 and a CH2, and they're tied back to this CH2. This bond and that bond are identical. It's not chiral, so you don't have to worry about inversion. Certainly if you want to draw the inverted attack, you can. But because the molecule is not chiral, it's the exact same thing. And so if you were to draw inversion, you'd look like this. SH would displace the Br minus. But whether you put the SH up or down would make no difference because it's the same thing. Where it becomes important is when you have a chair conformer that's chiral. If, for example, I drew, let's draw a different one. Let's put an iodine. And suppose I had a methyl here. Suppose I have a methyl there. Well, now these 2 carbons are different. I have actually, if this is out front, I have shown the chirality. Okay? So, there you go. Make that a little thicker. I've shown the chirality. Here's my carbons. I've shown the chirality here. And if I hit this with a strong nucleophile, like let's try, well, I don't know, this time let's use ethoxide. Sodium ethoxide. Remember, CH3CH2O minus could have a counter ion. So let's make the arrow go that far. And you'll throw in a solvent. Probably ethanol with it. This is my nucleophile. What kind of alkyl halide do I have? I have a very good leaving group, iodine. The carbon bearing the iodine has 2 carbons, so it's secondary. Secondary alkyl halides can go either SN1 or SN2. Because they can go either SN1 or SN2, I look at the nucleophile, while the alkoxide is a strong nucleophile. Strong nucleophiles, and let's just add this. Pause for a second and think about this. This is a salt. What do? Take a chunk of the salt and pour the cyclohexane on it? No, salts are dissolved in things. What would I dissolve ethoxide in? If I wanted ethoxide to be my nucleophile, what kind of solvent could I use? What would happen if I dissolved ethoxide in water? Well, if I dissolve ethoxide in water, ethoxide's a powerful base. What's going to happen is the ethoxide's going to come in and it'll come in as CH3CO2 minus. And it'll grab a proton and leave as methanol. And when you have a solvent, the solvent's usually present in huge excess. So what that means is there's going to be a few molecules of methanol, but there's going to be tons of water. And when it grabs a proton, what does the water become? Well, the water becomes hydroxide. So you're now going to have hydroxide present, right, in a lot of water, and there's going to be a little ethanol. The odds of this hydroxide hitting the ethanol molecule, because there's so little of it, is really low. So the hydroxide will exchange protons with other water molecules, and all you'll ever have in solution is hydroxide. So effectively, if I take ethoxide and dissolve it in water as my solvent, I get back hydroxide. I get hydroxide. There won't be any ethoxide in solution. Ooh, I got a problem. So what do I use as a solvent? Well, what I use as a solvent is the conjugate acid of the base. CH3, CH2, OH. Now, if ethoxide deprotonates ethanol, what do I get? Well, I get CH3, CH2, O minus. So I can, in reactions, if I'm not going to use something like aprotic solvent like acetone, I never use water as my solvent. I use the conjugate acid of base, because if ethoxide deprotonates ethanol, I get back the ethoxide. So ethoxide's always present in solution. So you'll often see as a solvent with ethoxide ethanol used. Now, ethanol is polar and protic. In this case, I do not want to use ethanol because polar protic solvents favor SN1. We'll talk more about this solvent factor later on in the course. But in this one, I'd probably use a solvent like acetone if I could. Okay. I might use aprotic solvents such as acetone. Of course, I have to be careful because other reactions, you want to make sure your nucleophile doesn't react with the acetone, which it can do. In this case, we'd probably be okay in spite of the fact that the alkoxide can induce a aldol type reaction. But we're not going to go there right now. So, we've got a strong nucleophile on a secondary alkyl halide. What mechanism does it favor? Coming back. Secondary alkyl halides go SN1 or SN2. In the presence of strong nucleophile, it favors SN2. If the chirality is shown, SN2 favors inversion, I have to draw the inverted product. In this case, you have to show it. The H comes down, and the O, CH2, CH3 is up. Now you might say, wait a second. We've got the big groups axial. The big groups are axial, and we know when you have large groups axial, it's the minor conformer. This guy can ring flip. Well, you can leave it like that unless you're asked to draw the most stable conformer. If you were asked to draw the most stable conformer, you would draw the ring flip structure. And the ring flip structure would look something like this. Now that methyl and the ethoxy group are equatorial. This is the same molecule, only ring flipped. Note, you do not have to draw this. You can tell that the OCH2CH3 here is inverted. The H has swung down to where the I was, and the OCH2CH3 is where the H was. We've shown inversion. If, however, I said draw the most stable chair conformer of the product, you could draw this, realize both groups are axial, ring flip, and get both groups equatorial. Easy to do. Not a problem. Okay. What do we get? What do we get if instead of that ethoxide, we used pure ethanol with no ethoxide present? Well, ethanol is a polar product solvent. This is a solvolysis reaction. Solvolysis is just SN1. Secondary alkyl halides can go either SN1 or SN2. Weak nucleophile favors SN1. What does SN1 do to a chiral center? SN1 would give you this guy plus, okay, if you like, it would give you both of those. This guy plus the product that didn't invert. Because what does SN1 do? It gives you racemization. Carbon, 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 carbon. And you would get a racemate. Now hopefully you're jumping up and down in your seat saying, wait a second, Dr. Lloyd, you just said if we do SN1 we have to draw the carbocation. Absolutely. You should draw the carbocation. You should have done that before you drew your product. Why? Well, let's draw the carbocation. Let's use this chair up above to draw our carbocation. When the iodine leaves, the H will go trigonal planar, and you'll get a plus here. You'll have the CH3 down, and the H here. There's your carbocation once that I leaves. Is there anything you can do to that carbocation? What kind of carbocation is it? The C, which has the plus, is 2 carbons, so it is secondary. It is a secondary carbocation. Okay, well, let's take a close look at it. Is there anything I can shift next door? Well, if I took some of the H's off the back and tried shifting an H, I'd then have a plus here. There'd be an H, and that would put an plus on a carbon that has 2 carbons, so that would be secondary. But what about a 1,2 H shift where this H shifts? And so this has gone trigonal planar. And you've got a plus here. What kind of carbocation is that? Well, there's a carbon here, a carbon here. You've got this carbon attached to the carbon bearing the positive charge. Carbon bearing the positive charge is tertiary. We've gone from secondary to tertiary. This is a more stable carbocation. That would mean, in this case, the OCH2, CH3 would not have gone on here for SN1. Okay. That would mean you'd have an H here and an H here. Where would it have added? It would have gone on here. Okay, so I get a racemate there, right? Well, you get a racemate there only if that center's chiral. Check it. Here's a CH2. There's a CH2. Here's a CH2. There's a CH2. They're both tied up to this back CH2. This center is not chiral, so you don't have to worry about racemization. It's the same thing. The shifting took away our chirality. Wow. I had to watch for shifting and then I lost chirality. Interesting. What about this chair conformer? Well, if you come over and you say, wait a sec, strong nucleophile, I've been doing a bunch, I don't have to worry about shifting, strong nucleophile favors SN2, I'm going to do inversion, our center's chiral, you're jumping the gun. You forgot to do something. What do you need to do? First and always check to see what kind of alkyl halide have. You have 3 carbons attached to this carbon. Put dots for my carbons. 3 carbons attached to that, so it's a tertiary alkyl halide. Tertiary alkyl halides go SN1 no matter whether or not you have a strong or weak nucleophile. So you have to look, you have to draw your carbocation and look, oh, terrible, terrible. That's better. You have to look for shifting. What kind of carbocation have I got? Well, I had a tertiary alkyl halide. I'm already tertiary. If I shift the H, you'll never shift from tertiary to tertiary. So there's no rearrangement. That's okay. The center is chiral. What does SN1 do to a chiral center? Now you get it. A racemic mixture. So we'll get the CH3 with the OH. And you would have to draw the other chiral center. And so the OH would be up then. And you get a 50-50 mixture. I will assume 50-50. You do not have to write 50-50 if you draw both structures. Okay? This would be drawn on scrap paper. I wouldn't see this. I'd just see your products. Let's try a more interesting structure. Put a Cl, change our leaving group a bit. And let's hit them with hydroxide. What kind of alkyl halide do I have? The chloride is attached to a carbon that has 2 carbons attached to it. So let's put dots so you can clearly see the carbons of the ring. 2 carbons attached to the carbon that bears the chlorine. This is a secondary. Secondary alkyl halides can go SN1 or SN2. We've got a strong nucleophile. We'll favor SN2. That would be inversion of the chiral center, but I have not shown the chirality. So you can just go ahead and draw the OH. And there's your product. Okay, let's try now water. Secondary alkyl halides in the presence of the weak nucleophile water favor SN1. Whenever you think SN1, you have to go to your scrap paper and draw your carbocation. So we'll go and draw our carbocation. Here's my carbocation. It's a secondary carbocation. 2 carbons are attached to it. Came from a secondary alkyl halide. Is there anything I can shift? Well, if I shift any H's off of this methyl right here, I'll be putting an H over there, getting a plus on the end. That'll be primary. Secondary will not shift to primary. But how about a 1,2 methyl shift? How's that look? One 2 methyl shift will produce this. Here are my carbons. That ring, so you can see them. Plus is now over here. The positives on this carbon, what kind of carbon is that? That carbon has 1, 2, 3 carbons. It's tertiary. Can secondary shift to tertiary? It certainly can. Tertiary is more stable than secondary. But when you do a shift, you always shift to the most stable carbocation. The reason for that simply is energy. The molecule will rearrange to the lowest energy state. 1,2 shifting occurs, the lower the energy of the carbocation, the faster that 1,2 shifts. So whichever 1,2 shift will give you the lowest energy carbocation, that one occurs. And I did say you can shift anything. I looked at this methyl because it's attached to this carbon, right? There's a carbon here. I'll put dots for all my carbons. Well, why did I shift the methyl? Attached to this carbon is also that CH2. Why didn't I do a 1, 2 CH2 shift? That is, shift the ring. See that bond here? Break that bond and shift it to where the plus is. In other words, that bond right here. Let's draw the bond in red. How about that? That shifted. That might make it stand out a little better. That CH2 shifts from this bond to make it here. Okay? It's shifted that bond. That's just like a methyl doing a 1,2 shift. The CH2 shifts over. What kind of carbocation is that? The plus is on a carbon that has 3 carbons bound to it. It's also tertiary. Ooh, we got the possibility of 2 tertiaries. Certainly, they should be the same stability. Except, you learned about something called ring strain previously. What kind of ring is this guy? It's a 5-membered ring. A cyclopentane ring. Cyclopentanes, if they were flat, would have bond angles of 108. There is some strain, albeit small, in a cyclopentane ring. If you could produce a more stable carbocation and reduce ring strain, you'd be gaining more energy back than just producing a tertiary carbocation would. Did we get to a more stable ring, reducing ring strain? Well, what kind of ring is this? If I count all the carbons, there's 1, 2, 3, 4, 5. There's 6 carbons in that ring. Let's draw that same ring structure a little different way. The molecule I'm now drawing is the exact same ring. And the plus is here. Oh, yeah. Whoa. That is a cyclohexane. A cyclohexane is a 6-membered ring that can go into a chair conformation with perfect 109.5 degree bond angles and every carbon having staggered hydrogens, totally minimizing angle and torsional strain, so the combined ring strain is to a minimum. The reduction in ring strain plus going to tertiary makes this 1,2-CH2 shift more favorable than the 1,2-methyl shift. And the 1,2-methyl shift does not happen. So now I've got to draw my product. Oh boy. Well, the product is simple. Where the positive is, that's where the alcohol goes. And I don't have to worry because I didn't show chirality here. Unless asked for, I would not have to show the chirality in the product. So I could just draw this as my product, unless I'm asked. But if I was asked, what would I have to draw? The OH actually went for the positive charge. the OH2, and then it was deprotonated. I'm not showing chirality, so this is sufficient. But if I was asked, show or represent all stereoisomers, I could do that with wedges and dashes. It would be based on this product. How could I show all of the stereoisomers? Well, that's pretty easy. If I had to draw the stereoisomers, I notice there are two chiral centers. The 1,2 shift, when it shifted the ring, scrambled this chiral center here. Because this carbon was that carbon. And it's still chiral. It has a methyl, a different carbon here, a different carbon, and an H. This center's chiral. So there are two chiral centers, which means there are 4 stereoisomers. If I had to draw all possible 4 stereoisomers for this, without drawing chair conformers, I could draw them like this, using dashes and wedges. Dashes and wedges. And so I could draw that. I should have drawn it over a little bit. I could draw just changing one of the centers. Draw that. I could switch the bottom chiral center now. Or I could take the original, keep the top chiral center unchanged, and change the bottom. So if I was asked to draw all 4 chiral centers, I could do that. So all 4 stereoisomers would form. All right. When doing 1,2 shifting, though, you do have to be careful. Why? Suppose I give you a molecule like this. And say I hit it with hydroxide. No, H2O. Let's do H2O. I have a secondary alkyl halide here. Secondary alkyl halides can go SN1 or SN2. I look at the nucleophile, see I have a weak nucleophile, I favor SN1. In SN1, you're supposed to look at the carbocation. So you're supposed to draw the carbocation, and you do. Say, okay, I'm going to draw the carbocation. and I do that. I draw the carbocation. Now, can I 1,2 shift? Well, I see I can do a 1,2 methyl shift. And if I do a 1,2 methyl shift, I would get something like this. And you have to ask what kind of carbocation you started with and what kind of carbocation did you form. Well, the carbocation obviously was like the alkyl halide. It was secondary. The carbocation that forms has 3 carbons attached. It's tertiary. Tertiary carbocations are more stable than secondary. Usually they are. But there is one exception. There is one carbocation that is more stable than even a tertiary carbocation. And that is a carbocation. I'm going to represent the tert-butyl by an R group, if that's okay. A carbocation, I'll just put an R for that big tert-butyl group here, that is resonance stabilized. I can draw all these resonance structures for this. Should double bonds are in the right positions. This carbocation is very stabilized because you remember in resonance, none of the individual resonance structures exist. What exists is a resonance hybrid, which is some averaging, if you like, of all the structures superimposed on each other. In other words, there's some averaging. And you end up with a delta plus, delta plus, delta plus. Partial positive charges in all those positions, wherever there was a positive. This is extensively stabilizing. This stabilizes even more than tertiary. Hence, our rule for saying that you shift only to more stable carbocations would state that this doesn't shift. Okay. Well, where does the nucleophile attack? If I look at all these resonance contributors, can the nucleophile, the nucleophile sees positive in all those positions. The nucleophile is attracted to positive. Will the nucleophile end up attaching to all of the positives? Well, you have one advantage here because of the aromatic ring. Aromatic means especially stable. Turns out this pi cloud of electrons repels the nucleophile because it's mainly negative charges. And to put the nucleophile on that aromatic ring would disrupt your aromaticity. You'd lose that stability, and that's a huge energy cost. So we are in luck. The H2O actually just attacks where the bromine is and does not attack where the delta plus positions are. So the nucleophile can't attack here, can't attack here, can't attack here, because that would disrupt aromaticity. It only can add on the benzylic position. And when you're done, all you end up with has OH here. And there is no 1,2 shifting, because the resonance stabilized carbocation is more stable than the tertiary. All right. How about this case? What if we have another resonance stabilized case? What if I have CH3, CH, Br, CH2, CH, double bond CH2. Well, here I have a secondary alkyl halide. And let's hit it with water. I certainly could add some groups. Let's put some more groups here, because we could put another CH3 . So let's try something like this. Okay, we have a secondary alkyl halide. The secondary alkyl halide can go either SN1 or SN2. We have a weak nucleophile which favors SN1. The SN1 reaction produces a carbocation. We can look at our carbocation. Draw the carbocation. Do I do a 1,2 shift? This is a secondary carbocation, just like the alkyl halide. If I shift this H right here, over to here, I'll get a tertiary carbocation. Does that happen? Well, the answer is no, because this carbocation is not just secondary, it's allylic. I can resonance stabilize that positive charge. Resonance stabilization means that neither of these structures exist. Okay, I'm going to use R for the isopropyl. So R is this CH3 twice CH. What exists is the resonance hybrid. This is what the nucleophile sees. The nucleophile sees what's really existing. Neither has a pi bond. What you have is a delta plus and a delta plus. The positive charge is spread at both positions. So when the nucleophile comes in and attacks, in this case it can hit either position. And so what do you get? While you can get the OH going in place of the bromine, so you can get OH here, or you could get the nucleophile H2O attacking that position, which would give you this guy. And you'd get an equal mixture, or very close to 50-50 mixture of the two. So in this case, resonance produces two sites of attack and prevents 1-2 shifting. Okay, let's erase this. And let's look at what this molecule would produce if it was reacted under SN2 conditions. Say using hydroxide. In SN2 you do not produce carbocation, so there's no resonance involved. Suppose we were to go hydroxide. Secondary alkyl halide favors SN2. There's no carbocation. But we get an interesting rare mechanism taking place because of the transition state in the SN2. Now if you remember the transition state, you would get backside attack. If I was to draw a transition state for this molecule, I would have the C, okay, and I'm going to make the BR down. I'm going to use R for the isopropyl group. So we'd have an H. I'm going to put my 2p, because in the transition state, we go sp squared. I'm going to make the hydroxide incoming. So let's draw the Br going off this way, just for the fun of it. Okay. I have over here another CH. I'll draw it like this. And off of it, I have my CH2. And I'm going to draw the 2p's there. These are the 2p's from the pi bond. Right? So this is my pi bond. Okay, bit of a labeled orbital diagram there. And we could have the hydroxide, HO, coming in and adding here. Delta minus, delta minus. And you say, well, that just forms the top product. So let's go ahead and draw that over here. So that's just the top one again. Br leaves. The OH, you get inversion, but I haven't shown chiral center, so you don't have to worry about showing it. There you go. But something weird and wonderful can happen here. Not just this. This certainly can happen. Backside attack, SN2, bromine gets kicked out. But something else can happen that effectively is caused by the side-to-side overlap of the orbitals. You'll notice that this 2p is side-to-side overlapping with this 2p, but also it will help stabilize this transition state side-to-side. There will be some side-to-side overlap, and the electrons can move throughout the side-to-side overlap. Is it not possible then to have the OH attack here and have the electrons move through the pi system where the bromine leaves? Effectively backside attack, but since these orbitals can move electrons back and forth where the side-to-side overlap is, could not the OH come in here and then electron density move this way through the side-to-side overlap of the 2p? Indeed it can. And that would put the OH at the other end, effectively producing for SN2 the same product distribution that we saw in SN1. But it doesn't do it by resonance. It does it by this unique backside attack that allows electrons to flow through the side-to-side overlap of the 2p's. and it shifts, and this becomes the new pi bond once it's left. This mechanism that produces this second product is called let me draw that again, SN2 prime. It's an SN2, but the hydroxide's doing its backside attack, not opposite the bromine, opposite side of bromine, but shifted down, allowing electrons to flow through the side-to-side overlap in the transition state. You must memorize this special case of the SN2 prime and be able to account for it. Okay, well, we've covered a lot of ground. We've done a lot of sample problems of substitution reactions. In the next lecture, we're going to be looking at the competitor to the substitution mechanism. We're going to be looking at eliminations, E1 and E2. I'm Dr. Brian Lloyd. This is my Scribblecast.